Hello everyone, here is our project which will discuss an experimental optimization of microneedle patch. We are Azhar Al Busaidi.
Maryam Al Amri.
And Victoria Scira.
The purpose of this project is to observe the fluid flow profiles of insulin drug delivery in a microneedle. The fluid profiles that will be tested in this experiment are pressure and velocity to prove that it is an efficient method of drug delivery compared to other drug delivery methods. The microneedle array are minimally invasive devices that bypass the striatum corneum barrier, then accessing the skin microcirculation and achieving systematic delivery by the transdermal route. The height of the microneedle array are usually between 50 to 900 micrometers. By using microfabrication techniques, the microneedle array are made with various geometric and materials, such as silicon, metal, and polymer.
So the idea for our project or microneedle arrays is to apply it on the skin surface, which can penetrate the epidermis painlessly. It creates microscopic aqueous pores for drug diffusion to the dermal microcirculation, which is used to deliver drug like insulin. The need and motivation of using microneedle patch are: it can deliver proteins, nanoparticles, and both small and large molecules through the skin. Microneedle patch allows less pain and frequency of DUDs. It increases user complaints. There are multiple ways to create these products, which are instantaneous release and slow release over time. So we decided to model the case of an instantaneous release of insulin in a microneedle patch.
The idea of our simulation is to show the velocity and pressure profiles based off of parameters from past experiments. Our COMSOL model represents what is happening in one microneedle and its associated drug reservoir. The equation below was used to determine the average velocities. From average velocity, we were able to find infusion rate, which were then able to find infusion pressure. And in this equation, N stands for number of needles, delta T is your infusion time, and we assumed it to be 1 second. And our needle length we chose to be 0.9 millimeters from literature values, and the pain threshold was 2 kilopascals, and our infusion amount was 7.66 units. Here are our two COMSOL profiles. The upper left-hand corner shows the velocity profile, and the bottom right-hand corner shows our pressure profile. Here is a 3D rendering of our velocity profile, and as you can see at the tip of the microneedle, our velocity is the highest. The red is the highest velocity, and the dark blue is the lowest velocity.
Here's our 3D model of the microneedle patch. The printed model dimensions are 7 by 7 cm, while the experimental one on COMSOL is 0.9 mm in length, since we based our experiment on one microneedle. The next slide shows a video of the microneedle patch model while it's being printed.
At the end, we can conclude that microneedle patch is painless, regulated drug release, and more efficient, and the microneedle transdermal drug delivery method is best compared to other methods of drug delivery. For future work, we will consider doing this experiment in a lab as clinical trial to really observe the pressure and velocity profiles of the fluid flow of insulin. This way, we can get more precise. Thank you for watching our presentation.